Hello everyone, welcome to the video for NTNU Drillbotics Phase 2 presentation for the year 2022. We're going to go through the table of content of this video. We're going to go through the NTNU Drillbotics team, the mechanical rig design, the BHA, the drill bit, the control system, the graphical user interface or GUI, the safety and human factors, the Duplins Curve, challenges and lessons learned, finance, and finally the sponsors for the project. My name is Luis Alvarez. I have a bachelor's in petroleum engineering from Colombia, and right now I'm pursuing a master's degree in petroleum engineering with a specialization in drilling. For this project, I'm the team coordinator, and I'm also in charge of the analysis for the downhole sensor.
My name is Michaela Solberg. I'm a drilling engineering student, and I'm primarily responsible for the drill bit design and HSE.
My name is Henrik Helgeland. I am currently pursuing a master's degree in petroleum engineering with specialization in drilling. My responsibilities in this project are well trajectory planning and finance.
My name is Jarl Nash. I'm studying a master's degree in cybernetics and robotics. I have a bachelor's degree in automation engineering from Bergen. And my responsibilities is control system and IT organizer.
The mechanical rig design will be briefly explained. First, we have the hoisting system, which is composed of the hoisting motor, which provides vertical displacement to the guide frame and to the rest of the drilling equipment. Next, we have the drilling system, which is composed of the top drive motor, which transmits rotation to the bit using an internal rod that travels all the way throughout inside the drill pipe. Next, we have the azimuth control system, which is composed of an azimuth motor, which transmits torque to a gearbox and then to a rotary table. This rotary table is connected to a drill pipe and allows the transmission of rotation to the BHA and to the bend sub at the bottom. This allows the steering of the bit at a desired angle. The azimuth control system also has a torque sensor in order to have control on how much torque is being applied and how far the azimuth it is. Finally, we have the circulation system, which is a semi-closed loop for hole cleaning. The circulation system is composed of a hose, which is connected to the hydraulic swivel, which avoids the water going all the way up to the drilling equipment and forces to go down through the drill pipe, all the way through the BHA, and finally exiting through the drill bit nozzles. Then the water comes all the way back to surface, going into the new implementation for this year, which is the diverter. The diverter allows the system to have control on the returns from the well. The returns will come from the bottom of the well to the diverter, and then if they will be disposed, exiting from this nozzle to a hose, which will allow the safety disposal of water returns and cuttings. This will avoid a wet floor around the rig and cement particles in the air, improving HSE for the system.
The BHA is designed to provide stability and steering capability while drilling. It also houses the sensor card and transmits torque from the rod to the drill bit. The BHA is composed of two stabilizers, a sensor housing, a bend sub, a universal joint, a drive shaft, a wear plate, and a bit sub. The upper and lower stabilizers counteract lateral drilling vibrations and provide stability to the drill string. The sensor housing is a thick-walled cylinder with a compartment that holds the sensor card. A two-part adhesive is used to protect the sensor card from the surrounding metal, water, and mechanical stresses. The BHA uses a fixed bend sub for directional steering. It enables the BHA to kick off and build a deviated well path. The angle on the bent sub is designed to reach the maximum inclination of 30 degrees required for the competition. The universal joint transmits rotation in the bent sub. The upper end secures the rod with 2 set screws, while the lower end is welded onto the drive shaft. The drive shaft runs from the lower stabilizer and attaches to the bit sub. A wear plate made of PEEK is placed between the bit sub and lower stabilizer to minimize the friction. Lastly, the bit sub provides a connection between the drive shaft and the drill bit. NTNU Drillbotics has a long-standing collaboration with Ling Drilling. The team is responsible for designing and modeling the drill bit, while Ling Drilling manufactures the final product. Last year's drill bit designs were analyzed and altered in the efforts to optimize the drilling efficiency. A total of 4 new drill bits were produced this year, and the following modifications were made. Firstly, the cutter density on the nose and shoulder were increased to limit the exposure of high drilling loads that may result in impact damage. Several cutters on the gauge were also adjusted to improve the force balance of the drill bits. According to simulations performed by Ling Drilling, this resulted in the unbalanced forces decreasing from 27% to 16%. The width of the blades on the bit face and gauge were increased to enhance drill bit stability and reduce vibrations. Next, 2 additional wear-protecting TSP inserts were implemented to each gauge pad to produce low-friction surfaces and improve drill bit durability. An extra TSP insert was also added to the nose of the bit as reinforcement and as a depth of cut limiting feature. After that, space was opened up in the center of the drill bit to add an extra nozzle for improved cutting removal. Lastly, the drill bits were hard faced with stainless steel for increased wear resistance.
The rig has 3 servo motors. The first is used to move the hoisting system, the second one rotate the bit, and the third one orientate the BHA. A load cell measures applied weight on bit to control the hoisting system, and the torque sensor is used to limit the maximum torque when orientating the BHA inside the rock. The downhole sensor is an Arduino Nano 33 BLH that is used to estimate roll and pitch. The control system is built in Simulink with MATLAB function and blocks. A digital twin is a virtual simulation of a physical system. The digital twin enables fast prototyping of the position estimation, well path generation, and reference path controllers. A Kalman filter is used for reducing the measurement noise from the downhole sensor. MPC, Model Predictive Control, is an advanced method of process control that is used to control a process while satisfying a set of constraints. In our case, it tells the azimuth where in the rock we want to go. UI is a graphical user interface. It's used to visualize the planned trajectory and what is the real trajectory based on measurements from the downhole sensor and the position model. Here is the position of the drill bit, the true vertical depth, the measured depth. Here is the orientation, also the rotation around the 3 axes, the azimuth, inclination. The rotation set point is telling where the azimuth will go, like left or right, and that's based on the MPC controller. The green one here is the well path, is where we want to go, and the red one is where we actually went.
Safety and human factors. HSE was the top priority for the team throughout the whole project. As a way to apply this, the team applied a risk analysis evidencing what would be the potential risk throughout the project and how to avoid them. As an example, we have the use of protective personal equipment or PPEs when we were drilling inside the lab, as seen on the picture on the right. Another way to implement the HCC was the diverter, as explained before. Another key factor that we keep into account throughout the whole project was the human factors. The way that the team applied this was to use, firstly, situational awareness in order to reduce any problems with communication throughout the drilling process. As an assistance to this, we assign fixed roles in order to have clear messages between the operator of the rig and the rest of the personnel. We also perform bow-tie analysis to the major hazardous events that we could have throughout the system, to have control measures in the prevention and recovery measures on the recovery to avoid any consequences for the hazardous event. Finally, we also apply pop-up notifications in the graphical user interface or GUI in order to keep situational awareness on the operator at all times, so we knew what we were doing throughout the drilling process.
3D Duplins curves are implemented in the control system for well trajectory planning. The trajectory is generated before a drilling operation starts, and the output will be the well trajectory that the NMPC controller will use as a reference. The main property of a Duplins curve is that it provides the shortest path between 2 points in 3D, using 2 curved sections and a straight section as shown in the figure at the top. The circular arcs are constrained by the maximum allowed dogleg severity given by the fixed bend sub in the BHA. To generate a full well path trajectory that includes all the different targets, several Duplins curves are combined in series as shown in the figure at the bottom. A dedicated cost function is used as an optimization strategy to minimize the total length of the trajectory with curvature constraints. The team has experienced several challenges and lessons learned throughout the Drillbotics project. One major challenge has been the sealing of the sensor card in the BHA. It has been a bottleneck in the project since it delayed the testing of the rig and the control system. The sealing of the sensor card is a time-consuming process, and it turned out to be difficult to get it completely waterproof. After multiple failed attempts using Tech 7 and epoxy, successful sealing was obtained using a polyurethane potting, which is less viscous compared to epoxy and therefore led to a better seal of the sensor card. In addition, the team experienced that the rod was slipping in the drill track due to wear of the jaws. As a solution, a stronger drill track with a better grip was acquired and implemented on the rig. As an additional preventive measure, the rod was milled down on 3 sides to increase the friction between the rod and the drill track jaws. There have been no major expenses this year since most of the rig components are reused from previous years. In addition, some of the components are not included in the budget, like for example the diverter, because it was produced in-house by the NTNU workshop and is therefore considered as an in-kind contribution. For these reasons, the team has managed to stay well within the budget limit of $10,000. As the presented budget shows, the largest expense is associated with a new computer with cabinet. The remaining expenses are of smaller size and include titanium rods, sensor cards and sealing, drill track, cement sacks, and a camera. To sum up, the total expenses in this project ended up at around $3,700. The NTNU Drillbotics is sponsored by Brew21, which is a research innovation program in digital automation solutions for the oil and gas industry. Equinor is also sponsoring the project, while Ling Drilling supports through manufacturing and delivery of the drill bits. We would like to thank all our sponsors for sharing their knowledge and financial support. This was NTNU's contribution to the Drillbotics 2022 competition. Thank you very much for listening.